Hi everyone, great to see you here. Today I'm going to talk about laser focus and its impact on accuracy of urinary isotopic dating. We probably all know that focusing is important. What we don't know is what impact poor focusing can have on the reproducibility of dating results, and how well we can do with focusing. We believe that error associated with focusing has been underestimated. We hope to raise awareness of this issue so to improve reproducibility of urinary dating within the community. LA-ICP-MS is an ICP-MS equipped with a laser ablation system for direct sampling of solid samples. A recent study showed that it can even be used to ablate liquid wine samples for trace element analysis. One of the most important applications is urinary geochronology in earth sciences. Accuracy of urinary dating by LA-ICP-MS has been constantly evaluated using zircon, a common and a robust mineral that is rich in uranium and thorium, but contains very low common lead. The figure here shows results of a blind test using a synthetic zircon sample. We can see that most data are accurate within 2% of the ID team's urinary ages, but some can be 4% too young or too old, with a total age variation of more than 10%. This figure shows results of another blind test on 2 magmatic samples. Overall, it shows that urinary dating by LA-ICP-MS has poorer reproducibility than SIMS, another technique widely used for in situ urinary dating. It is essential to understand what the error sources are and how much they contribute to the uncertainty. Recently, a few studies systematically examined the matrix effect, air, laser fluence, laser pulse width, etc. Little attention has been paid to laser focusing. So, what do we know about laser focus in terms of its impact on urinary isotopic dating? So this study, published on applied spectroscopy in year 2000, showed that focal position variation by 1000 to 1500 microns can lead to substantial changes in ablation pit dimensions and the laser irradiance. Correspondingly, urinary ratios changed as well. A more recent study showed that while all other parameters remain constant, a much smaller focus position variation of 30 micron only can already change the rate of ablation slightly. An age bias of 1.5% was estimated as a result of this change. The authors suggest that other than bottom roughness, no obvious modifications in shape and diameter of the ablation pits can be observed using conventional optical inspection. So we carried out similar experiments recently, but found obvious modifications in shape and diameters as is shown here. Figure C clearly shows that as the focus gets worse from on focus to 30 micron out of focus on both ways, the pits becomes bigger and the bottom becomes rougher. We increased laser pulses to 205 and employed a confocal laser scanning microscopy to estimate the depth of ablation. Due to increased surface roughness at the bottom, the uncertainty in estimating depth of ablation was high. Overall, we can see the depth of ablation decreases when laser becomes increasingly defocused. This is as expected. So we employed 2 different LA-ICP-MS systems to directly determine the age bias solely from defocusing. I'd like to highlight that with the conditions used here, the total depth of ablation was only about 10 to 12 micron. Here in figures A and B, we show that slow variation of laser focus can lead to a systematic offset in lead-206 to uranium-238 ages. The ages of zircon samples tend to get younger when samples are out of focus. Variation in trend lines can at least be partly attributed to matrix effect and uncertainty in focus position determination. In figure C here, we have all trend lines aligned, and you can see that the edge bias is up to 6% for edge samples when laser is focused 30 micron below or above sample surface. In figure B, we can also see that focus variation by up to 40 micron has little impact on that edge determination. So we also analyzed NIST 610, rutile, titanite, and their results are compared with that of zircon GJ1 in figure D here. We can see little impact on NIST 610 glass, but an edge bias of up to 12% arises for rutile when laser is focused 30 micron below or above sample surface. Also, the edges of rutile sample tend to get older when samples are out of focus. Height variation is intrinsic for samples distributed across a laser ablation cell. The chance that all samples in the ablation cell sit exactly on the same plane level is rare. We noted that sample heights can still vary even if they are next to each other. The reason for sample height variation vary from one case to another. It is random. So there is a need to focus samples separately. We did this test to understand the reproducibility of manual and autofocusing commonly used. We agree that samples can be focused to 10 or even 5 micron within that of the sample surface. However, expertise and significant efforts are required. Also, while most position readings are within 10 micron, that of the laser focal plane, the error can be 30 micron or bigger. Ultimately, an improved microscope system is needed for highly precise and effortless focusing. However, before such a system becomes readily available, users should examine the topographic conditions of their samples and check alignment of parts within ablation cell carefully. Alternatively, users should use a large spot size and or limit the depth of ablation where possible, as is illustrated in A here. Raw lead to 6 to uranium 238 ratio of GJ1 zircon standard show different Dahol fractionation patterns at different focus positions. The difference is negligible in the first few seconds of ablation and gets bigger as ablation continues. This pattern is better demonstrated after Dahol fractionation calibration here. We show in figure B that the impact of focus position variation on uranium isotope fractionation can be limited by reducing the time. Well, it is essentially the depth of ablation or increase the spot size of ablation. We can see here the edge bias gets smaller from red here, which represent 27 seconds of ablation, to light orange, which represent 10 seconds of ablation. With 7 seconds of ablation, the edge bias also gets much smaller when we simply increase the spot size from 20 micron to 40 micron. I like to draw my conclusions simple as below. Uncertainty in focus position determination can lead to a significant drift in determined uranium isotopes of natural minerals commonly used for dating by LA-ICP-MS. Therefore, we suggest that sample focus should be checked intensively during experimental setup. And bigger spot size, lower laser fluence, and fewer laser pulses should be applied where possible to minimize the impact of inaccurate focusing. Thank you for your time.